Top 100 Unsolved Mysteries of the Universe. Episode 3. Quantum Cosmology and the Problem of the Universe's Initial Wave Function. Picture a strange scene. Galaxies, stars, dust, the arrow of time, and even the rest of cosmic history have not fully unfolded yet. But physicists already want the first page of the script and initial wave function for the whole universe. A master quantum state from which the later universe can be derived. The ambition sounds magnificent. The trouble is that the usual scaffolding of quantum theory disappears the moment the object becomes the entire universe. When we talk about a wave function in the lab, we quietly assume there is a system being studied, an external clock ticking in the background, an apparatus that will eventually register an outcome, and some observer standing outside the setup long enough to say what was prepared and what was measured. But if the system is the whole universe, who is outside to prepare its initial state? Who is the first observer? What counts as the measuring device if every device is already part of the thing being described? And if time itself is still part of the problem? Where exactly does the t in the equation come from? That is why the phrase "the universe's initial wave function" looks like a clean starting point question while actually bundling object definition, boundary conditions, probability interpretation, and measurement grammar into the same black box. Mainstream physics has proposed elegant answers, no boundary ideas, tunneling pictures, choices among different vacuum states, but they share a familiar awkwardness. Before explaining why the universe began the way it did, they often end up quietly choosing the opening poster in advance. Before explaining who reads the probabilities and how the readout becomes real, they have already written the probability distribution on the board. It is a bit like trying to draw one grand spectrum for the entire ocean while forgetting that there is no calm shoreline outside the sea where you can first set up a camera, a ruler, and a clock. EFT approaches the problem by changing the status of the wave function itself. It does not begin by searching for an even more mystical cosmic wave function. It first rewrites what a wave function is allowed to mean. In EFT, a wave function is not the ultimate ghost behind reality, not a sacred cloud hanging in darkness before the universe switched on. It is closer to a compressed ledger or navigation file. Once the C state, the boundaries, the grammar of the apparatus, and the available channels are fixed, that ledger records which paths are allowed, which phases can be reconciled, and which outcomes carry greater weight. The ledger is useful, sometimes indispensable, but the ledger is not the universe itself. That flip is crucial, because it turns the whole question around. Instead of asking, what did the universe's initial wave function look like? EFT asks, in that early, high-tension, strongly mixed energy sea, before stable clocks existed, under what boundary conditions could certain structures appear first, certain channels open, and certain readings later be written into cosmic history? EFT adds a second guardrail that matters just as much. The observer is inside the universe, not outside it, and measurement is not a godlike glance from beyond but a material process of insertion, coupling, threshold crossing, and bookkeeping. Once you accept that, it becomes clear why importing the ordinary package of external observer plus ready-made time parameter plus ready-made probability interpretation straight into the origin of the universe is already a grammatical mismatch. EFT does not smash the mathematical tools. It reorders explanatory authority. The mainstream wave function can still survive as an effective computational language, but it no longer automatically occupies the throne of the universe's primal ontological manual. What has to be rebuilt first is the material working condition of the early energy sea, how its overall rhythm slowed, how channels opened, how boundaries filtered possibilities, and how local repeatable records and structures emerged out of boiling noise. In that picture, the cosmic beginning looks less like choosing an abstract state vector and more like walking into a factory floor that has not fully cooled yet. Some regions are so violent that they do not yet deserve to be called clocks. Some boundaries act like gates that allow only certain modes to survive. Some fluctuations get amplified into later seeds of structure, while others die directly in the noise. So the initial condition problem is no longer which abstract exam paper did the universe pick first. It becomes which C conditions and boundary grammar baked the later world into existence. It is not a search for a baby photo of the universe. It is a return to the delivery room and the workshop to temperature, pressure, medium, exits, gates, and rhythms to see how the first stable records could be produced at all. In EFT, time is not a pre-laid background river but a readable count of repeatable beats. The wave function is not the God behind the universe but the compressed navigation map written by boundaries and channels. And the starting point is not primarily a choice of one cosmic state vector, but a material chain of early conditions that could actually manufacture a visible history. That is EFT's central rewrite of the initial wave function problem, not drawing a more mystical total wave function for the universe, but dragging a heavily mystified question back onto a mechanism chain that can be built, interrogated, and connected to the real working conditions of the early universe. Tap the playlist for more. Next episode, the universe's low entropy initial state problem. Follow and share our new Physics Explainer series will help you see the whole universe more clearly.